Theorem, let f be a continuous function on a solid region Q defined by the value of x between two constants a and b, y between two functions of x, h1, h2, and finally z, a function of two variables, g1 of xy, g2 of xy. All four, h1, h2, g1, and g2 are continuous functions. Then we can define the triple integral over the solid region Q for the function of three variables based on the change in volume as these three integrals integrated, they're iterated integrals, and we're going to order them dz, dy, and dx. Let's look at our first example. We're going to integrate with respect to x from 0 to 2, integrate with respect to y from 0 to x, and then finally integrate from 0 to x plus y with respect to z. Inside, we have the function e to the x times y plus 2z. If we take the antiderivative with respect to z, then that gives us e to the x times y z plus z squared over 2, which will cancel that 2, times e to the x. It's totally appropriate if you want to distribute that e to the x before you take the antiderivative with respect to z and then factor it back out, but this is what you would wind up with. Since we took the antiderivative with respect to z, z will catch the x plus y and the 0. Substituting in, we have e to the x times xy plus y squared, and again that's z replaced with x plus y. This z, when it becomes x plus y quantity squared, that means we're going to write that twice and FOIL. That will give us x squared plus 2xy plus y squared. Now we still have the differentials dy dx, and we're down to two integrals. Still working from inside out. Oh, also before I forget, I combined like terms, and that gave us a pretty good reduction. Now, taking the antiderivative with respect to y, we have e to the x, x squared, y, e to the x, 3x, y squared over 2. And again, I'm leaving the e to the x factored out. So basically, each of these three terms take the antiderivative with respect to y. So that's 3x y squared over 2, or 3 halves xy squared. And then this term will be y cubed divided by 3 times 2. And the y's will all be replaced with x and then with 0. Substituting in x, that gives us x cubed. And again, I'm going to leave e to the x factored out. X squared times x, that's x cubed times 3 halves. X cubed times 2/3. Excuse me. 1 plus 3 halves plus 2/3. If we add all that up, that comes out to 19/6. I pulled the constant out, x cubed. This is going to give you some Calculus 2 flashbacks. This is an integration by parts. We have an algebraic term multiplied by an exponential term. So we would let u be x cubed, dv would be e to the x. This is one of those where it takes a while to chisel down your algebraic term. In fact, you would have to use integration by parts 3 times to get it all the way undone. Once you do that, the integration by parts 3 times will lead to these 4 terms in the expansion. We will still have e to the x and our 19 over 6. Substituting in 2 and 0 for all the x's, we're going to get e squared times 8 minus 12 plus 12 minus 6. So that's 2e squared. And then when you sub a 0 in for all the x's, you get a 1. E to the 0 is 1. Zeros for these 3 terms minus 6. So negative 6 times 1, that's positive 6 because we're subtracting it. And so that leads to 19 thirds e squared plus that 6 and that 6 cancel, leaving 19. 19e squared over 3 plus 19 would be your exact answer. If you approximate it, it would be just shy of 66. If we switch to cylindrical coordinates, then the triple integral over our solid region Q with respect to a 3-variable function times the change in volume will be in this format. Recall, here's our conversions for cylindrical and rectangular. Those will come in handy setting up your integral later. I want to point out this r here is very easy to forget it. So you'll have a function in cylindrical coordinates where x is r cosine theta, y is r sine theta, z stays the same, and you'll integrate with respect to z, r, and then theta. Example, find the volume of the solid region Q. Cut from the sphere, x squared plus y squared plus z squared equals 4, by the cylinder, 2 sine theta. I didn't do a super good job of drawing this diagram out. If you check your e-text, it's 14.7 in your e-text. You can find a better diagram of this. I just did the best I could. This is symmetrical if you were to rotate this. Now, the reason I'm pointing this out is theta, remember in cylindrical coordinates, is the angle swept from the positive x-axis, which is 0 to pi if you make a 180. In cylindrical coordinates, your r, which is your middle differential, is 2 sine theta. So we're going to integrate the r term, well, the r with respect to r from 0 to 2 pi, or excuse me, 2 theta. Our sphere is equal to 4, but due to this conversion, we can change x squared plus y squared to r squared, and that'll give us r squared plus z squared equals 4. Solving for z, because that's the only integral we haven't set limits for, subtract r squared, you got 4 minus r squared. Take the square root, and that will be the positive and negative square root of 4 minus r squared. And as a reminder, r is from 0 to 2 sine theta, and theta is from 0 to pi due to being swept out. This is that little r that I was careful to point out up here. It's very easy to forget that. Now, to ensure positive values, and since Q, that solid region, is symmetric on the xy plane, that means this portion and that portion will have equal volumes. I'm going to double the integral, but I'm going to cut that theta in half. So instead of from 0 to pi, I'm going to go 0 to pi over 2, only looking at that much. But as long as I double it, it covers the same ground. The rest of the integral stays the same. So now we take the antiderivative with respect to z. We have rz evaluated at these two. We have r square root of 4 minus r squared minus negative r square root of 4 minus r squared. Well, that's 2r square root of 4 minus r squared. The derivative under here, because if we're going to take the antiderivative with respect to r, underneath the radical, that derivative should be present out here. Because I'm going to use u substitution, I'm going to let u be 4 minus r squared. That derivative is negative 2r dr. Well, we have 2r dr, we just didn't have the negative. So I'm going to put a negative here, but you have to balance it out with a negative out here. Now, this becomes u to the half. The antiderivative of u to the half is 2/3 u to the 3/2. 2/3 u to the 3/2. And we're gonna, now I returned them from u back to the original r variable, so I didn't have to change these integral limits. Substituting in 2 sine theta for r, followed by 0 subbed in for r. I'm also moving 2/3 out. Negative 2 times 2/3 is negative 4/3. Now with the substitution, we have 4 minus 2 sine theta quantity squared. That's 4 minus 4 sine theta, minus 4 minus 0 squared, which is 0 to the 3/2. To simplify this, to the 3/2 power, that's the square root of 4 minus sine squared theta cubed. Factor out a 4. Pythagorean identity lets you change to cosine squared. That square roots to 2 cosine theta. To the 3rd power is 8 cosine cubed theta. 4 minus 0 is 4. Square root of 4 is 2. Cubed is 8. Now I'm going to move the 8 out and reverse the order. And that'll make this lead coefficient positive. So factoring out an 8 makes negative 32/3, but reversing the order due to subtraction, that becomes positive. I'm going to rewrite cosine cubed as cosine times cosine squared, and this is the work over here in the red. Pythagorean identity, you can switch that out for 1 minus sine squared theta, and that'll give you cosine theta minus sine squared theta cosine theta. And that's the switch in here. So from this step to this step, just see the side work in the red. The antiderivative with respect to theta will be theta minus sine theta. This part is another u sub. If I let u be sine theta, its derivative is cosine theta d theta, which is precisely the rest of the problem. The antiderivative of u squared is 1/3 u cubed. 1/3 u cubed. Replace theta with pi over 2 and 0. That's going to give you 32/3. Pi over 2 minus sine of pi over 2, that's minus 1, plus 1/3 sine of pi over 2 cubed. Sine of pi over 2 is 1 cubed, still 1 times 1/3. And then when you plug a 0 in, all these terms go to 0, because you'll get a 0 here. Sine of 0 is also 0. So that's why I just made a big 0 here. Complete the math, and you will get 16 pi over 3 minus 64/9. If we look at a triple integral in spherical coordinates, this is the part to look out for. Our outer integral will be based on theta, and that's from angle 1 to angle 2. Theta stays the same. It's the angle swept out around from the positive x-axis. Phi, or phi, however you want to pronounce it, is the middle differential. Phi, remember, that's the angle that comes down from the positive z-axis. And then finally, rho, that's the distance from the origin. For convenience, I put in the conversions from rectangular to spherical. And let's do an example. Find the volume of a solid region Q bounded by the upper nap of the cone, z squared equals x squared plus y squared. And I tried to embed that cone inside a sphere underneath and bounded above by the sphere x squared plus y squared plus z squared equals 9. Due to our conversion, we can make an easy trade here. These three variables can become rho squared, and that gives us rho equals 3. The equation of the cone and sphere, we can replace x squared plus y squared with z squared. And that's what I made a note of here. The equation of the cone, the equation of the sphere. To find the intersection, we look at where they're equal. So that's 2z squared equals 9. Divide both sides by 2, and then take the square root. That's 3 over square root of 2. And that's where those two graphs intersect. Now to address phi, the angle coming down from the positive z-axis, that is going to be, phi is the arc cosine or cosine inverse of z over rho. So we can set that up. Z was 3 over square root of 2. Rho was 3. So dividing by 3, multiplying by a third is the same operation. Cancel your 3's. 1 over square root of 2, rationalized, gives us a familiar number from the unit circle. Cosine inverse of square root of 2 over 2 is pi over 4. And so that's the angle down from the positive z-axis. Okay, so as a reminder, rho is going to be between 0 and 3. Phi or phi is going to be between 0 and pi over 4. And theta, because this is a full rotation, is 0 to 2 pi. So in order, theta, put its values in, phi, put its values in, lower and upper limits, and then finally rho, 0 to 3. Take the antiderivative with respect to rho, that's rho cubed over 3. That's going to catch a 3 and a 0, so 27 over 3 is 9 sine of phi. 0 cubed just goes to 0. Antiderivative with respect to phi is going to be a negative 9 cosine phi. Evaluated at pi over 4 and 0. That's going to be, and I'm going to pull this negative 9 out front. So negative 9 times the integral from 0 to 2 pi. Cosine of pi over 4 is square root of 2 over 2. Cosine of 0 is 1. So square root of 2 over 2 minus 1. That's a constant. The antiderivative with respect to theta. Oh, let me point this out too. I did that trick of reversing the order, and because it's subtraction, I negated the lead coefficient. This is a constant, so its antiderivative will be the constant times theta. Subbing in 2 pi followed by 0 is going to be 18 pi times this constant minus 9 times 0 times the constant. So there's really a minus 0 out here that I didn't write. Distribute 18 pi, you get 18 pi minus 9 square root of 2 pi, and that's approximately 16 and a half. I hope this video helps. These triple integrals are very tedious, and it's not the easiest to set the integrals up if you're given the equations of two figures and you have to come up with all three constraints, I guess is the way to say it, for your integral. But once you get it set up, then usually you can plow through and do okay getting it completed. Reach out if you have any questions or concerns. I check email frequently. You're more than welcome to call, email, stop by the office, and I will check out on this video. And again, I hope it helps you.